Section 10.4, which is all about the hyperbola. Our goals for today are that we can find the key features of a hyperbola, write an equation of a hyperbola in standard form, and graph that hyperbola. Let's start with the definition. A hyperbola is the locus of points where the absolute value of the difference of the distances from two fixed points, which are called the foci, is constant. So this point right here, the distance from that point to this focus minus the difference from this point to this focus is going to be constant regardless of where you put that point on either branch of the hyperbola. Some key features of the hyperbola. Hyperbola, because it has two curves or branches, is going to have two vertices, here and here. The segment that connects them is called the transverse axis. It is similar to the major axis in the ellipse, but it won't necessarily be the longest axis in the hyperbola. The conjugate axis, right here in this light blue, is perpendicular to the transverse axis and has the co-vertices as endpoints. This again is similar to the minor axis of an ellipse, but it may not be the shortest axis of the two in a hyperbola. The midpoint of these two segments is the center. And the foci, here we have one focus and the other focus, are going to lie on the line that contains that transverse axis. Every hyperbola will have two asymptotes. You can see these orange dotted lines here that will pass through the center. And also, the asymptotes pass through the center. Okay. Each branch of the hyperbola is going to start next to an asymptote, go through a vertex, and end next to the other asymptote. This box here, in kind of this turquoisey type color, is what I call the guiding rectangle. It passes through each of the vertices and the co-vertices. It's really helpful for making your graphs because once you have that guiding rectangle, your asymptotes will just become the diagonals of that guiding rectangle. And once you have your asymptotes and your vertices, you can sketch in the two branches of a hyperbola. Just like our other conic sections, there is a reflection property for hyperbolas. If you reflect something starting from one focus of the hyperbola, reflected off of one branch of the hyperbola, it will reflect to the other focus of the hyperbola. Some places where you can see hyperbolas. Planes that fly faster than the speed of sound will generate a sonic boom, which is a cone-like wave. Where that cone intersects the ground is one branch of the hyperbola. The sonic boom will hit every point on that curve at the same time. No one outside the curve is going to hear the noise of the sonic boom, but everybody on the inner part will. And occasionally, because of humidity, you can actually visibly see the sonic boom. If you have an open-top lampshade, you can actually see the shadow on the wall. Here's the top branch and the bottom branch of a hyperbola. Hyperboloids, okay, which is like a three-dimensional hyperbola. That when you take the cross-section of the three-dimensional shape, that is a hyperbola. And they're sometimes used for making gears. This one is interesting to me because I used to live very close to a nuclear power plant. When engineers are trying to design these towers, they have two main issues to keep in mind. The structure needs to be able to withstand high winds, earthquakes, tsunamis, tornadoes, all of these things. It has to be a very strong structure. And you want to, for economic reasons, build it with as little material as possible. And the hyperbolic form addresses both of these. One of the nice things about this is you can actually construct this shape with straight beams. It would not be a very strong structure if you had to curve the beams in order to create this curved shape. But by offsetting each of these beams, you can have straight beams, pour concrete around them, and generate this shape here. Some architects like to use parabolas and hyperbolas. In fact, the Dulles Airport is a hyperbolic paraboloid, which means if you take a cross section one way, you're going to get a hyperbola, and if you take it the other way, you would get a parabola. The Cassegrain reflector uses the properties of both the parabola and the hyperbola. So this type of telescope will have a parabolic primary mirror and a hyperbolic secondary mirror. So information coming into the telescope will reflect off of the parabolic primary mirror, go to the focus, the shared focus of the parabola and the hyperbola, which will then reflect off of the hyperbolic mirror back to the second focus of the hyperbola, which is located just outside the eyepiece where you would be standing, so that you get a very clear visual image. This allows you to have a much smaller compact telescope, but a stronger power, visualization power. And many of you have actually eaten a hyperbolic paraboloid because those are Pringle chips. Yum.